Okay, hello everyone, and welcome back to the YouTube channel and to this power system analysis session. And if you must remember, a few days ago we started a series of videos about introduction of DC transmission systems. Initially, the idea was dedicate those videos to my students, but then I say, okay, what if we start to having some guest lectures in this YouTube channel? And I say myself, what if we have very important people coming to the YouTube channel and presenting the topics? What if better that if we have people that write books, write very good papers, and have experience on HVDC systems, and they come to the YouTube channel and deliver a class for my students and also for everyone in YouTube. And the first name that came to my mind, to be honest, it's Professor Vijay Sood. Vijay Sood. Vijay Sood, he has been a close collaborator of myself for a few years. I remember a few years ago, a PhD student, Harold Chamorro, he's a Colombian guy. He introduced me to Professor Vijay Sood, and we start to write papers together. And I believe there are also some book chapters together. But he's a very famous guy, and in terms of HVDC systems. As you must remember, at the very beginning of these classes and those videos, I present several good books, and I make a connection with one of his book, HVDC transmission conversion applications in power system, and I remember this book because this is the recent one in HVDC transmission system of Professor Vijay Sood. However, there is a very good book about HVDC system and facts, and I used to learn HVDC reading his book. That is the book of HVDC and facts, application of static converters in power system. He is author and editor of those books, and I believe he has enough background to be a very important person in HVDC system. And I say, okay, let's invite Professor Vijay Sood to my YouTube channel and deliver a class for everyone. It's not only for my student, it's for everyone around the world, okay? And Professor Vijay Sood was so kind, very friendly, and he said, yes, let's do it. And to be honest, without any hesitation, 3 days later, we were recording the video, and right now I am excited to release this video to the general public, okay? But before we start to run the presentation, let me present a short mini biography of Professor Sood, okay? He is in Ontario, Canada. He is on the other side of the wall, and he is at Ontario Tech University, okay? He is a registered professional engineer, and he is a life fellow of the IEEE, one of the biggest achievements in your CV, life fellow of IEEE, fellow of the Engineering Institute of Canada, and emeritus fellow of the Canadian Academy of Engineers, okay? He has extensive expertise in HVDC transmission system and facts, flexible AC transmission system, okay? Also including the controllers of those devices, okay? His research is focused right now in monitoring, control, and protection of power system and the integration of renewable energy system into smart grid, okay? Professor Vijay Sood has an extensive reputation. He has many publications, many citations, and as you can see over there, he is the author of 2 books. I mean, nobody else has better experience to talk about the topic that he will deliver today, okay? And What I will do now is I will ask Professor Vijay Sood to start the presentation, and I will say thank you very much to all of you watching this video. I hope you enjoy this very knowledgeable person and his presentation. Professor Vijay Sood, the environment is all of yours. Please deliver your presentation.
All right, welcome to this presentation on high voltage DC transmission systems. In particular, we will talk about high voltage DC controllers. My name is Vijay Sood, and I will walk you through this presentation. So here is a HVDC converter bridge. It is a 6-pulse converter bridge, and we are going to analyze this in some more detail. But before we do the analysis, we want to make some assumptions about this 6-pulse converter bridge. This is the workhorse for the high voltage DC transmission systems. Normally we will have 12-pulse bridges, but here, just for the theory part, we are focused on a basic element, which is a 6-pulse bridge. So the assumptions that we are going to make first is the DC current, ID, is going to be remaining constant. We have 6 valves. These valves are shown over here as a thyristor. But in reality, of course, in a valve, we have many thyristors in series, which comprise the valve. So these 6 valves are indicated as T1, T3, T5, T4, T6, and T2. This is the attached AC system. The AC system is assumed to be strong, i.e. it's an infinite system. Therefore, the AC voltage does not vary. The 3 phases are indicated, EA, EB, EC. The commutation impedance is indicated as LC. This could be part of the transformer, which is connected to the converter bridge. And this could be the inductance of the transformer, or it could be a separate inductance which could be added in. So this is the basic HVDC converter bridge. We have the DC voltage indicated as VD, the current ID. LD is the smoothing reactor, which maintains ID as constant. It's a fairly large value. We can assume that it's a large value, so therefore the DC current does not change very much. LC is the commutation inductance. Usually it is of the order of 15 to 18% of the transformer, which could be connecting these AC system to the DC system. To look at the equation for the rectifier, when we assume this 6-pulse bridge, if the 6-pulse bridge is acting as a rectifier, then this equation describes the behavior of that rectifier. VDR is the rectifier voltage, is equal to VDOR, which is the open circuit voltage of the 6-pulse bridge. The angle, the firing angle, is described as alpha, and the cosine of the angle. So this voltage over here is a variable voltage as a function of the firing angle. Then the commutation voltage drop that takes place is indicated by RCR times ID. RCR is defined as 3 over pi omega LCR. And the open circuit voltage VDOR is described by this equation over here, 3 over pi √2 times V line to line, which is the line to line AC voltage. If the converter is operating as an inverter, then we can have either one of two circuits. The first one is using an angle beta, which is equivalent to the firing angle or the delay angle. And the inverter side is shown over here, and the DC voltage of the inverter is indicated as negative. The DC current comes in, voltage drop across the inductance, which is the commutation inductance of the transformer at the inverter end. And this equation then describes the behavior of this circuit. We can have another variant to this. We can utilize the angle gamma instead of beta. Gamma is the extinction angle at the inverter. So if you use that variant, then this sign changes over here, and this equation now describes the behavior of the inverter. There are some more details about the inverter end. So beta is defined as 180 degrees minus alpha is equal to mu minus gamma. Mu is the commutation angle, which is described by the voltage drop over at the inductance. So either using beta or gamma, we have this equation. With beta, we have equation number 2. So these two circuits can define the behavior of the inverter. Normally, we utilize this configuration to keep the reactive power consumption, to reduce the reactive power consumption. The extinction angle is maintained constant at the inverter. So these two equations again describe the behavior, and they are linked in this fashion. And this graphic over here, you can see that cosine minus cosine of gamma, cosine beta minus cosine of gamma. This sine wave over here is a projection of the cosine of the angle alpha. Alpha is on the horizontal axis over here. The vertical axis is the cosine of the angle. So when you look at this, you can see that the angle beta, okay, is calculated as 180 minus alpha is given over here. So this is 180 degrees from there minus alpha, which is counted from there. This will give you mu plus gamma. And this describes, this projection over here describes cosine of beta, cosine of gamma. And the difference between them is indicated as k times ID, where small k is a constant. We can see that how these two are connected. So the connections between gamma and beta are described in this graphic. The functions of the controls, HVDC controls, are as follows. Their primary objective is to control the power flow between the two terminals, the two DC terminals. They also must protect the equipment against any current or voltage stresses caused by any faults. And finally, the controls must also stabilize the attached AC systems against any operational mode of the DC link. So in here we show a two-terminal HVDC system. There could be a transmission line or could not be a transmission line, i.e. this could be a back-to-back connection, connecting two AC systems, AC system 1 with AC system 2. In red over here, we see the controls. And the controls are broken down into master controls and local controls. So we have a dispatch center where a power order could be sent over to the master controller. The master controller will just convert these into local variables like DC current or DC power, and then send that to the local controls. The two local controls for the rectifier inverter may or may not be connected by telecommunications. If you want fast behavior of the system, then you'll need to have some kind of telecommunication link. The telecommunication link is not necessary, but you can still operate the DC system without telecommunication, but it has to be a very slow operation in that case. So here are the primary functions for the DC controllers. First, they must limit the maximum DC current. This is in order so that the valves have a very low thermal inertia. So any kind of excessive current in the valves could be dangerous for the valves. So we must limit the maximum DC current. Typically, this could be limited to maybe about 1.2 per unit value. But beyond that, the valves do not like having too much current going through them. The second objective is to maintain the DC voltage to make sure that we do not exceed that certain maximum value. Again, insulation requirements determine what is the maximum DC voltage for transmission purposes. We want to have a maximum voltage because we want to maximize the power flow. So in order to keep the flow of power as high as possible, we want to maintain a high voltage. But there is an upper limit to how we can exceed that, how we can reach that maximum limit. And finally, the controls have the objective to minimize the reactive power consumption at the AC side of the system. Minimizing the reactive power consumption means that the angle, the delay angles, and the commutation, and the extinction angles must be kept as low as possible. So we summarize in this table the requirements for the DC link. The requirements are split into two. We look at steady state requirements and dynamic requirements. Firstly, on the steady state requirement, one of the objectives of the controllers is to limit the generation of non-characteristic harmonics. Every converter generates harmonics. Normally, the characteristic harmonics are, when you analyze the behavior of the converter, you see that the characteristic harmonics like the 5th, the 7th, 11th, and 13th, etc., are generated. These are normally, the normal behavior of the converter will generate those. The non-characteristic harmonics are all the other harmonics. And we want to make sure that we limit the generation of those non-characteristic harmonics. The second requirement over there for the DC link is to maintain accuracy of the controlled variable, the DC current or the constant extinction angle. At the rectifier end, it's the DC current. At the inverter end, it's the extinction angle. And we want to make sure that those can be accurately controlled. Finally, we want to cope with normal variations in the AC system impedances due to any topology changes in the system. If the AC system, the interconnected AC systems that we have feeding into the DC link, if there's any change in the topology of that system, then there will be changes in the AC voltages. So we want to cope with those kind of those changes. On the right-hand side of this table, we have the dynamic requirements of the DC link. So the dynamic requirements are any changes in the flow of power current. We want to make sure that we can start up the system from zero. We can absorb any fault-induced transients. We also want to make sure that we can reverse the power flow in case we have a back-to-back system. Not so much in a two-terminal system, but in a long-distance two-terminal system. But in a back-to-back, usually sometimes we want to have the reversal of power flow. So we want to be able to make sure that we can do that. Finally, we want to be able to tolerate the frequency variations of the attached AC systems. So when we look at all these variable requirements, we can come up with a control strategy for a two-terminal DC link. So here are the desirable features for the controllers. The first requirement is to limit the maximum DC current. As we discussed earlier, this is for the protection of the valves. The valves have a very low thermal inertia, so we do not want to have too much current, extra current flowing in the valves. So in order to protect the valves, the maximum DC current must be limited. This suggests a control implementation that in order to have a constant current controller at the rectifier would be the best control mode. The second requirement is to employ a maximum DC voltage. The reason for this is to reduce the power transmission losses. The higher the voltage that we can have, we maximize the flow of power. So therefore, we want to make sure that the transmission losses are kept low. The control implementation to achieve this requirement is to have a constant voltage control at the inverter. The third requirement is to reduce the incidence of commutation failures. In line commutated converters, a commutation failure is a fairly frequent incident, and we want to make sure that we reduce that as far as possible, obviously for stability purposes. In order to do that, to minimize the incidence of commutation failures, the control methodology that is suggested is to use a minimum extinction angle control at the inverter. So if we can keep a minimum extinction angle, then the possibility of commutation failures will be reduced. The fourth requirement for the system is to reduce the reactive power consumption at the converters, both at the rectifier end and at the inverter end. And in order to do that, the reason for that is for economic reasons, is to make sure that the voltage regulation of the AC systems is minimized. And the control methodology that is suggested for this is to utilize minimum firing angles. So alpha and beta should be as low as possible. So these are the control implementation requirements which are suggested for these reasons. So how do we achieve this? All right, so how do we implement that control strategy? So in this graphic over here, we have the rectifier shown in red and the inverter in blue. So let's talk about the rectifier side controls first. This graphic shows you the VD-ID characteristic of the controls. Now, the line AB, this line over here, represents the rectifier operating with minimum angle, firing angle alpha. This is a direct extraction from this equation over here, equation number 1. So this is a direct implementation of that. If you look at this, this represents a straight line with a slope, a negative slope, right? The axis will be intercepting over there. So you can see that implementation as this line AB shown over here. This line BC over here represents a constant current characteristic. If you looked at the requirements over here, we said we want a constant current controller at the rectifier. So to implement this characteristic BC is implemented. So now you can see that the equation number 1 defines the line AB, and the line BC represents a constant current characteristic. This area over here represents the operating area, the operating zone for the rectifier. Superimposed on this is the characteristic for the inverter. And you can see this line P and Q. Line PQ represents the same kind of behavior, which is defined by this equation number 3 with a negative slope, and the angle gamma that defines a straight line with a different slope, and that is this line PQ. Again, to implement a constant current characteristic for the inverter side, we impose this line QR, this characteristic over there. So now you can see that the rectifier has this characteristic shown in red. The inverter has this characteristic shown in blue. And wherever these two characteristics intersect, that will be the operating point for the DC transmission system. So for instance, this point X over here defines the operating point for the two converters. The rectifier is operating on constant current characteristic. The inverter is operating on its constant voltage characteristic, or the constant extinction angle characteristic. And this point X now defines the operating point for the transmission system. You can see the two characteristics over there shown as the we can see over here a difference in the constant current characteristics of the rectifier and the inverter. These are separated by something called delta I, which is the current margin. And sometimes this control philosophy or this control methodology is also called the current margin control philosophy. So you can see that the current setting at the inverter end is lower than the current setting at the rectifier end. Typically, this value could be about 10% of the settings. So if this is 1 per unit for the rectifier, then the inverter would be getting a current, constant current characteristic at 0.9 per unit, so that we have a 10% margin indicated over here. So normally what happens is now the DC transmission system will be operating at this point X. Sometimes what happens if the AC voltage at the rectifier changes, if it drops down by a certain value, then this characteristic over here, AB, can shift downwards. And if that happens, then the operating point will move from X to Y. And this way, if the operating point is at Y, you can see now the inverter will take over current control, and the rectifier will be on this dotted line over here, which is the alpha min characteristic of the rectifier. So that will take over the voltage controls for this way, the control strategy will be changed, but you can still operate the system at almost 0.9 per unit current and almost at full voltage. This could be a change in the voltage by 10% or so. So you can see that the control strategy can switch from the rectifier to the inverter, but you can still maintain transmission if there is any kind of fluctuation in the AC voltage at the rectifier. So this is the normal characteristic for a HVDC system. We can implement some more changes, some more modifications to this system. Those modifications are shown over here. So what are these modifications? You can see over here, the maximum current limit is shown as 1.2 per unit. So we don't want to exceed that. This is the protection system that we want to make sure that the valves are safe. This characteristic, which is the AB characteristic, is also called the alpha min limit characteristic for the rectifier end. This characteristic PQ, which is shown over here, is the constant extinction angle characteristic, and the operating point is indicated. The margin is there, and we have this characteristic for the inverter. But now we modify this characteristic. I am just going to change and point out this characteristic over here. You can see now that this characteristic has been changed, and this is the constant beta characteristic that we can implement. And why do we need to have this modification? So sometimes what happens is that if the AC voltage at the rectifier drops by a few percent, then this operating point shifts from X to Y. The controls can have multiple operating points if this characteristic is very steep. For instance, let's say if this characteristic is something like this, the slope is quite steep over here, and that slope is a reflection of the commutation impedance at the inverter end. Now you can see if the operating points will now be, they will be X, there will be another operating point at this point over here, and then there's an operating point over there. So now you can have multiple operating points, and this can be a problem, especially when you have a weak AC system operating at the inverter end. In order to avoid that, we modify this characteristic and put this constant beta characteristic for this portion. So the controls can do this quite easily with limits, so that we avoid having multiple operating points at this point over here. All right, so this is called the voltage dependent current limit. So it keeps it fairly low for the rectifier if the voltage should collapse for some reason. And finally, we have this modification over here, which is the minimum current setting, which is typically around 0.2 per unit. This is again a minimum limit which the valves do not have. The valves do not like having current zeros. So what happens is if the current in the DC system takes up this kind of approach, we have harmonics on the current and we have current zeros taking place over here. So we want to make sure that this minimum current is above this value, so we don't get these current zeros due to the harmonics in the DC current. This causes high voltage stresses related with the current extinction, and in order to protect the valves, we impose this current limit over there. So this is now the characteristic for an HVDC transmission system with a modified characteristic. Okay. So these modifications help to protect the valves, helps to protect the DC transmission system, and they are a very useful part of the transmission system. Here is a graphic of a HVDC control system from the actual installation. You can see these controllers. These are digital controls. So this is a view of the controls. So what are the current loops that we have discussed? So at the rectifier and the inverter, we have two settings which give you the ordered current, which is called IOR at the rectifier, IOI at the inverter. We have the ordered extinction angle, gamma naught, at the inverter. This method, like I indicated earlier, is also known as the current margin method of control. It employs PI regulators. There are some known problems with PI regulators. One of the problems is that these regulators used fixed gains. There is some possibility for some gain scheduling to take place. It is difficult to optimally select the gains. And even if the gains are selected, they are only optimal over limited range only. Since the HVDC system is continually changing, the PI controller settings are therefore not optimal over the whole range of operations. So these are some of the limitations that we know. But nevertheless, PI regulators are known to be very robust. They're very simple and they do a good job. So in HVDC systems, most controllers are PI regulators. So here are the controls at the rectifier end. So how does the current control work at the rectifier end? So here is the ordered current setting. We have a measurement of the DC current. There's a DC CT which is placed in the ground side. Normally it's on the ground side. It doesn't have to be, but normally it's on the ground side. The measurement of the DC current is taken and then compared to the ordered current. A current error signal is generated, and the PI controller has two gains, the KP and the KI, or it has a constant K and a time delay, which is time delay period, which is T. So this is a PI controller normally. This generates a firing order. which goes into a voltage control oscillator, and a ring counter follows that. So the ring counter purpose is to take the pulse train coming out from the voltage controlled oscillator and distribute the firing pulses to the various valves inside the converter. So this is the rectifier and current controller. Now, at the inverter, we have a similar control system. So we have a measurement of the DC current. That is taken and compared with the ordered value of the rectifier current order. So you can see that these two are the same. We have to subtract the current margin from this value. Remember, we were talking about this current margin over here. So the current rectifier order is set at this value, minus the margin gives you the current order at the inverter. So we generate an error signal. We go through a PI regulator again, 2 gains, and then we go into the voltage controlled oscillator and a ring counter to distribute the firing pulses to the converter. But at the inverter, we also have another controller. We have 2 controllers. This is the extinction angle controller. So in order to operate with 2 controllers over here, now we have to select the minimum firing order based on the current control or the gamma controller. So we have a min select circuit, and then we select the firing order and then go through the system. So this gamma controller over here is shown next. Over here, this is the gamma controller. So you can see over here that we have a gamma reference setting. We measure the gamma. So to measure the gamma, we have to have the valve voltages monitored. We select the minimum of the 12 valve voltages in a 12 pulse bridge, for instance. This is a min select circuit over there, so we want to make sure that the minimum gamma is selected. We compare these 2 values. We generate a gamma error signal. We go through a PI regulator and then into the current controller, which comes from the other side. So this is the gamma controller. And in order to measure the gamma, the valve voltages are required. And this is a variation of how we can generate the value for the gamma measurement circuit. There are 2 variations. One is the predictive method of control for gamma. The second is a direct method for the actual measurement of extinction angle. Different manufacturers have proposed different techniques. So here is the direct method. So you can see that when, for instance, the firing pulse for valve 3 is given, that is the point which we need to detect. We look at the valve voltage and we detect when the valve firing pulse is given. We set up a delay circuit over here, and that delay circuit is generated by this angle mu, which is the commutation angle. So the commutation angle, as soon as the valve 3 firing pulse is given, then the current in the valve number 1 starts to be taken down. It goes down to 0, and this period over here, for that current to go down to 0, from 1 per unit value to down to 0, is the commutation angle for that valve. This is the anode to cathode voltage, the valve voltage for valve 1. So once the current has gone down, now the voltage, reverse voltage is seen. So we detect this point, and at this point we initiate a timing signal, and this will now give us an indication for the gamma value that we want to set. So here is the measurement for gamma, the reverse voltage which appears across valve 1. This is the gamma measurement, so we can utilize this gamma measurement in the controllers over here. So this is one of the variations. The predictive method of extinction angle is proposed by a different manufacturer. So this is one variant, and this is another one. We will not discuss this one. So here is the hierarchy of the controls, the DC controls. So this is a bipolar DC system. We have 12 pulse bridges over 2 6-pulse bridges in series, giving you a 12-pulse operation. Usually the transformer connections are indicated star delta, delta, star star, star delta for the upper bridge. Usually the neutral on the star point is grounded. Over here, you can see the two valve groups. So the controls which are tied with this valve group, so these are the valve group controls. These controls which operate on both the valve groups are indicated as pole controls. And then finally we have the bipole control. So this is a bipole, so the positive pole and the negative pole, the neutral connection. So this is the positive pole, negative pole, and this operation which takes place over the whole bipole. These are the bipole controllers. So we have three levels of controls. So here are the 3 levels of controls. So we have a dispatch center which will give us a power reference order. This will be sent over to the bipole controller, which will communicate that information to the remote bipole. From here, we will generate the current order. So we need to have a voltage measurement to divide the power by the voltage to generate a current order. This will be sent to the 2 pole controllers, and then this will be split into 2 for the valve group controllers. So this gives you the hierarchy of the controls. So these terms, the bipole controller, the pole controller, and the valve group controllers are shown in this graphic. So here, this graphic indicates the monitoring of the various signals, how they take place in a DC system. So here is a indication of the AC side, the AC bus, the transformers going into a 6-pulse bridge. This gives you a 12-pulse operation. So this could be a pole. The negative pole is not shown. So you can see over here, this is the DC side of the link. So we have a requirement to measure the DC voltage. So there's a DC PT, which will measure the voltage at the DC bus. For any pole differential protection, we can monitor the currents so that we can have some kind of differential protection added in. The DC current is monitored. The AC current rectified, which is coming in from the AC side, is also monitored. So these currents over here, these are three-phase currents. These are monitored. We rectify those in here and then convert that to a DC signal. The DC CT over measures the DC current as well. So these two can be compared, and you can give an indication to the valve group protection system. This monitoring over here can also be utilized for overcurrent protection. So we monitor the currents coming in to the transformer, the currents going out of the transformer. These can be compared. So a differential protection scheme can be utilized. So here we can utilize this current and compare with this current to give us an overcurrent protection system. So various protection systems are indicated for the DC system. We monitor also the AC voltage. There's a PT over here, so that can monitor the AC voltage. You can monitor the AC current as well. So these can be linked into the circuit breaker for protection for any kind of fault on the DC system. So these are the various monitoring signals. So in order to protect against overcurrents, these are the three types of protection that we utilize. First is the current extinction, CE, a commutation failure or a misfire in the system, any short circuits internal or in the DC line. So we can protect against these kind of faults by using these control systems. So internal faults, which are fairly infrequent, the fault current can go up to 10 per unit level. The valve is usually rated to withstand this for a single shot. So the valve will take this kind of current, but these are fairly infrequent faults. A DC line fault, these are fairly frequent because DC lines are fairly long. They're open to lightning strikes and so forth. The fault current level will be typically 2 to 3 per unit. The protection methodology that's going to be used is what we call the forced retard of the firing angle. We change the firing angle from typically 15 degrees alpha to maybe 145 degrees very quickly. We can change the firing angle. So we can go into inverter operation at the rectifier. And this way we can reduce the DC fault current. The second thing that will also apply will be the dynamic VDCL, the voltage dependent current limit. So if there is a DC line fault, of course, the DC voltage will collapse. The low voltage protection at the rectifier will kick in. And this is the protection system that we talked about earlier. It's this characteristic over here, this VDCL characteristic. And this will protect against any DC line fault current, so the current is not exceeded. So finally, the third line of protection is to trip the AC breaker after a third attempt at making sure that the DC current is not excessive. So if the DC current persists, then the AC breaker will be tripped to protect the system. In terms of the commutation failure protection system, and these are fairly frequent faults, misfires, the fault current level typically for the DC current will be 1.5 to 2.5 per unit. A single commutation failure is usually self-clearing. The controllers will just ride through it. However, if the multiple commutation failures take place, then the beta angle will be advanced in stages, and the VDCL characteristic will kick in to make sure that the current is reduced to protect the valves. So this is the protection against overcurrents. For protection against overvoltages, this graphic shows you where the voltage arresters, the nonlinear voltage arresters are used to suppress any excessive voltages. So we have valve voltage arresters at various locations. Here, the filters will have their own protection. The valves will be protected against any overvoltages, so you will have surge arresters at all points. From the pole side, you will have surge arresters over there. These will be utilized for converter voltages. The DC arrestor, there's a reactance, there's a voltage arrestor across that one. There's a DC line protection system. There's an arrestor across the DC filter as well. And then if there's a neutral, so the neutral arrestor will be also, the midpoint arrestor and the neutral arrestor will be there. So various arrestors are utilized against overvoltages, and these are all shown over here. All right, so that closes the topic on high voltage DC controls for two-terminal systems. So in this presentation, what we have done is we have discussed the controls for high voltage DC systems. We've given you a brief introduction to how they can be utilized to control the system, and also how they can be utilized to make sure that they protect the DC system as well. So in closure, you can reach me at this email. If you have any comments, I would be more than happy to hear from you. So with that, thank you very much for listening to me, and goodbye for now.
Well, thank you, Professor Vijay Sood, for his amazing presentation on controls, HVDC controls, and in HVDC transmission system. Thank you very much for your presentation. I am really excited, and I am really grateful that you delivered this talk. And he is the first invited to this YouTube channel, and I hope we can have him back very soon with another interesting topic. Okay. I would like to say to all the viewers, thank you very much for watching this video. Please contact me or contact Professor Vijay Sood if you have any question or any suggestion. And we are looking forward to having more guest lectures here in the YouTube channel. I already sent an email a couple friends, very big names on HVDC system, to talk more about the HVDC transmission system, and hopefully they will reply very soon, and they will be some other guests here in the YouTube channel. Okay. Also, there are a few other colleagues that they already say yes. There are a few more surprises coming in the YouTube channel. And thank you very much for watching, and see you in the next video. Thank you.